This video is to demonstrate the apparatus and data taking for the spherical mirror experiment. So in front of me, I have the apparatus that you will need. So this silver box here is the laser ray box. We have our curved mirror here, so it is reflective on both sides. You'll need a protractor, which is provided, and a ruler as well, which is not provided. I got this one in a 3-pack from the dollar store, so those can be attained quite easily. And then this is the power supply for the laser box. So first of all, the laser box does not have an on-off switch. So in order to control whether the laser is on or off, you would simply need to plug it in or unplug it. So the other end has a power adapter, and that will plug into this side, and then the laser comes out from this side here. So before you plug it in, make sure that the laser is flat on the ground, that you're not looking directly into it. Although it is a low-powered laser, you always want to avoid having the laser beam going directly into your eyes. It's also a good idea to remove any jewelry, like rings or watches or bracelets, that might accidentally cause reflections to go into your eye whenever working with a laser. So I've plugged in the power on the other end, and now I'm going to plug in my laser. And I can see now that I have a red laser beam coming out here. And at the moment, I have a lamp turned on just to light things up. The rest of my room has the ceiling light off and the curtains closed. And you will find it is helpful to do this experiment in darkness as much as possible. So when I turn off my lamp, you can see the laser beam much more clearly. Now, you're also provided with these lined pieces of graph paper in your lab kit. And these are very helpful for this experiment. So the larger thick lines are in 1 centimeter squares, and then you've also got smaller subdivisions in 1 millimeter. So I've started already by drawing a long black line, and that is what I'm going to use as my paraxial line. So when I want to set up my mirror, then I want to set it up like figure 1-1. So I want to place it on my graph paper, and I want to make sure that the center of the mirror is centered on this paraxial ray. So the first step is to adjust the laser beam so that it is in line with the paraxial line that I've drawn. And notice right now we can see a reflected ray. So what I want to do is arrange the mirror so that the reflected ray is going right back on top of itself. And that way I know that my mirror is centered around the paraxial ray. So it is forming a 90-degree angle, and the light is reflecting right back onto itself. Another safety note is that you always want to observe this experiment from the top down. So you do not want to place your eyes at the level of the laser beam, and you do not want to be looking into the mirror because the light will reflect back into your eyes and could cause damage if you look at it for too long. So all of your observations should be from the top down. So when you are satisfied that your mirror has been centered around the paraxial line, then you want to mark the points A, B, C, and D on your mirror to make sure that you can place it back in the same position if necessary. So just now I know my mirror is where I want it to be, so I'm just going to move the laser out of the way for the moment. So I want to mark A That is the front or the inside of the concave part, so that's this side. And I want to mark the back, so that is the convex side. And then I want to mark the two corners. So up here and down here. So I'm drawing some lines. You can use dots if you prefer, just so that you're able to put the mirror back where it was if you need to move it or if it gets bumped out of the way for any reason. So I'm going to place the mirror back according to the markings. And then the first part of the experiment is to verify the law of reflection, which says that the angle of incidence is equal to the angle of reflection. So I want to plug my laser back in. And now, instead of having it along the paraxial line, I want to tilt my laser so that it is off the paraxial line. And I want the laser to reflect off of that center point. So I want the laser to reflect off of point A in figure 1-1. And now we can see the incident beam. So that is this beam here. And then we have our reflected beam over here. Now the mirror is not perfect, so we are getting a little bit of spreading of light. Now, the procedure states that you should use a pencil and a ruler to mark the incident and reflected beams. So remember that the rules for your lab notebook are that you must always write in permanent ink, the one exception being when you're doing things like drawing graphs or, in this case, drawing a diagram. And it'll be difficult to get a ruler in here to draw those straight lines. So what I recommend doing is drawing a few dotted lines with your pencil so that you can basically fill in the blanks when you turn off the laser. So just going to draw some dotted lines. And for my reflected beam, I'm just going to do the best I can to mark in the center of the laser beam because it is spread out a little bit. So I've drawn a few points, and I'm just going to turn my lamp back on so you can see them a little better. So I've drawn a few points here with my pencil, and now that this is out of the way, I can use my ruler to draw the straight line. So based on my dotted lines, doing the best I can to get a straight line here. Looks like about there. And so now I have an estimate of my incident beam and my refracted beam. So you want to include this diagram as part of your lab report. And anytime you are including a diagram like this, you want to make sure that it is labeled appropriately. So you could label it with the incident beam and the reflected. And you also want to give your diagram a title so that the person looking at this diagram would understand the purpose without having to ask you any questions about it. And now for the measurements here, you are going to take your protractor and you want to be careful to put the center on the paraxial ray at that point A, so where the front of the mirror met the paraxial ray. And you're going to use the protractor to measure these two angles. So from the paraxial ray to the incident beam, and then from the paraxial ray to the reflected beam. Now, the protractor has divisions of 1 degree, as well as small divisions of 1/2 degree. So you'll want to take that into consideration for your reading uncertainty using the protractor. And You also may want to consider any other possible sources of uncertainty, like, for example, physical uncertainty, because depending on your mirror's surface, you may have had to estimate where the center of the beam was and trying to connect these little dotted lines that were drawn when you had the laser beam on. So whenever you're doing measurements, you always want to consider all possible sources of uncertainty. So definitely going to have reading uncertainty for the protractor. And depending on your setup, you may want to include some physical uncertainty for drawing the beams as well. And once we've made that measurement for the front, or I guess I'm calling it the front, it's the concave side of the mirror, then what we want to do is use the other side, so the convex side of the mirror. And so I'm going to use my markings for my mirror position, and I'm going to put it back in place. And I'm going to turn off my lamp so I can see the laser a little bit better. And now what I want to do again is aim the laser at the point on the back of the mirror. So this was point B in figure 1-1. And just like we did in the previous step, I want to draw a line for the incident beam and the reflected beam. And it would be difficult to get a ruler in here to draw these lines. So what I'm going to do, if I can hold the laser in place, what I'm going to do is take my pencil and just draw a few dotted lines so that I can come in with a ruler afterwards and then draw a straight line. So got everything in place here. I'm going to do a few dotted lines. And my reflected beam is a little bit spread out, so just do the best I can. To first of all, try not to move anything, and second of all, to estimate where the center of my reflected beam is. So I'm going to draw in a few dotted lines here. So do the best you can, and now I'm done with that, so I can move the laser out of the way and turn my lamp back on. So again, take the ruler, draw in a straight line to represent the incident beam and the reflected beam. Again, I would recommend that you label the relevant information. So this is our incident beam. This is our reflected beam. And then again, you want to take your protractor and center it on the paraxial ray, and then measure your angle of incidence and angle of reflection, and taking into account all possible sources of uncertainty. So you'll definitely have a reading uncertainty due to the size of divisions on the protractor, and you may also want to include a physical uncertainty for trying to draw in those lines as best as you can. So in the next part of the experiment, we are going to find the focal length of both the concave and the convex side of the mirror. And we are going to do this by generating a series of parallel rays. And we're going to do that by, so I started with a clean sheet. I drew in a new paraxial ray. And conveniently, the graph paper has a whole bunch of lines on it. And so all of the lines that are going horizontally here are going to be parallel to this paraxial ray. So I want to choose 5 different positions for my laser beam and examine the reflected ray here. So what happens is the reflected ray will cross the paraxial line at a distance of the focal length from the concave and convex side of the mirror. Or sorry, just the concave side. Convex side is a little bit different. So I want to choose 5 different positions. So I could start maybe over here, and making sure that my incident ray follows one of the lines on the graph paper. And I can use my pencil to draw in a little dotted line, just like I did before, for the reflected ray, paying special note to where it crosses the paraxial line. Then I'm going to choose a different parallel ray and do the same thing. So indicate this was here, do some dotted lines, and now I'm going to go on the other side of the ray, draw in a few dotted lines here. And what you should notice is that you're getting a sort of convergence where all of the points are crossing the center line at the same place. So near the end, I'm not really bothering to draw in all the dotted lines. I'm just marking where it crosses the center line here. And when I remove the laser and I turn my lamp back on, then I can see I've got a series of points along the paraxial line here. And the average of the distance from these points to the front of the mirror will give us the average focal length for your mirror. So you want to make measurements using a ruler from the center of the mirror to each one of these places where the ray crossed the paraxial line. And so my closest one looks to be 2.11, and my furthest one is about 2.60, I would say. So you want to measure all of these distances and then calculate the average of those distances in order to determine the focal length. And just like in the previous part of the experiment, you want to label this diagram appropriately and include a copy of this with your lab report. So for the convex side of the mirror, we are going to use the same idea, although the drawing that we have to make will be a little bit different. So I'm going to flip this around and put the mirror back in place. And I'm going to turn off the lamp and turn on the laser. So again, I want to generate 5 parallel beams that are incident on the convex side of the mirror. And I want to sketch the reflected beam. So I'm going to draw a few dotted lines here. And you can see that these are not going to cross the paraxial line. But what happens is if we extend these lines backwards, then we can see where it would cross the paraxial line. So included a few dotted lines here so that I can safely extend this line backwards. Now I'm going to put the mirror back in and generate a new reflected beam. So again, making sure that my incident beam is parallel to the paraxial line. It's not necessary to draw the incident beam. I'm going to put in a few dotted lines for the reflected beam here. And move this out of the way and use a ruler to extend it backwards. And so similar to the concave side of the mirror, you'll get, hopefully, these lines will start to cluster around the same point. And you want to measure the distance from the convex side, so that would be this side here. You want to measure the distance from here to where that reflected beam would have crossed the center line. And again, you'll want to average all of those values to include an estimate of the focal length of the convex side of the mirror. And again, we are using a ruler, or this ruler in particular has centimeter markings with millimeter divisions. It's pretty standard. So you'll want to consider the size of the smallest divisions when estimating your reading uncertainty, and then include a physical uncertainty for anything that may have contributed in this case. So trying to estimate where the center of the beam is, drawing the line, connecting your little dotted lines, that type of thing. And that's how you'll determine the focal length of the convex side of the mirror. So for the final part of the experiment, we are going to measure the center of curvature for the concave and the convex sides of the mirror. So in order to save some paper, I just recentered the mirror at a different point on the page. Now, what you want to do in this case is, with the mirror centered around the paraxial line, you want to choose 5 positions for the laser beam where the incident and the reflected beam are right on top of each other. So in this case, the laser beam is forming a 90-degree angle with the surface at that point. So I'm looking for the laser beam and the incident beam of the laser and the reflected beam to be right on top of each other. And I'm just going to mark that line with a few dotted points so that I can then fill it in with a ruler afterwards. So that gives us one line, and I want to repeat this for multiple different angles of the laser beam. So if I try on this side, then again, I want the incident and the reflected beam to be right on top of each other. So there's another good one. Put in a few dotted lines. And then fill it in with the ruler. Making sure that you extend the line so that it crosses the paraxial line. And get a few more of these. There's another one. And eventually you'll see that these lines tend to converge near the same point on the paraxial line. So I'm just going to turn my lamp back on. And now the measurement that you want to make is to measure the radius of curvature. So you're measuring from where your incident or reflected ray, they're actually the same in this case because they're one on top of the other. You want to measure the distance from where that crossed the center paraxial line to that front side of the mirror. So I've only drawn in 3 rays here, but you should do a total of 5. So measuring these 3 distances, or 5 in your case, and averaging those 5 in order to get a measurement for the radius of curvature. And then we want to repeat this using the convex side of the mirror. So I'm going to recenter my beam, turn off the lamp, and shift things a little bit this way. And I want to do the same thing in that I want to find 5 positions for the laser where the reflected beam comes right back at the same angle as the incident beam. So I can choose this position here. Oops, bump my mirror, put that back. All right, making sure that my mirror is centered and making sure that the incident and reflected beams are right on top of each other. Draw in a few dotted lines. And just like we did with the focal length, you'll want to then extend that line backwards so that it crosses the center line or the paraxial line. So extend it all the way back. And these are getting quite close, so I'm just going to mark this as convex for that line. If it helps, you might maybe want to use a different color pen or maybe just use a different area. Now pick a different position. And again, I want the reflected and the incident beam to be right on top of each other. So this is a good position here. Using a few dotted lines to mark where the laser beam was, and then using a ruler to extend that line all the way back to the center or the paraxial line. And yes, this is going to get quite crowded, so you can see here, I've got one of these convex lines here, the other side is here. So it might be beneficial to use a new area on your graph paper so that you aren't mixing these up with the concave side measurements. But again, you're going to measure from the front of the convex side, so that's this point here. You want to measure from here, from this point here to where the convex line crosses the center. So this was one of my convex lines. Measure that there and do that for a total of 5 rays and average your measurements, making sure that you're including reading uncertainty from the size of the divisions on the ruler and then potentially a physical uncertainty for any other possible sources of uncertainty in this experiment. So for this lab, I have provided a blank template to help you organize the necessary calculations. And fortunately for this first lab, there aren't too many complicated calculations that are required. But I have set up this Excel spreadsheet because we will be taking the average of a set of data, and Excel has some nice built-in functions to help you calculate that more quickly. So you can access this template from the Lab Moodle page, and you'll want to make sure that you rename the file. So instead of template, you'll want to put in your first and last name, and you also want to fill in the relevant information that is highlighted in yellow here. So fill in your name, student number, and the date. And what I have here are blank spaces where you can enter the data, and then some more blank spaces that you can use to type in Excel equations or formulas. So you can store data in Excel as text or as numbers. So all of these labels are just written in text form. And when you want to enter your data, so I'm going to enter some sample data. Note that these are made up numbers, so don't expect yours to be the same. I can enter in some numbers. So if these were my measured focal lengths, like 5.12, 5.20, notice that Excel will automatically drop the trailing 0. You do not need to worry about keeping appropriate significant figures on your Excel sheet. The only time you need to worry about your sig figs are when you're recording the data and estimating the uncertainty, and then at the end when you are writing out your final results. So you don't need to worry about rounding anything off on your Excel sheet. So some more measurements filling in. We've got 5.40 and 5.60. And let's just say the uncertainty was 0.2 centimeters for all of those measurements. Now, the nice thing about Excel is you can grab the bottom right corner and use it to copy values either vertically or horizontally. So I just want to copy this value in the rest of these cells, so I can just grab and drag it down. And then I've included a column here for a calculation of the fractional or the percent uncertainty. And this is useful when it comes to the discussion of your precision. So whenever you are looking at the precision in your experiment, you want to identify which measurement had the highest percent uncertainty. And in this experiment, all of our measurements were distances in centimeters, but this will become more important when you're measuring values, particularly that are in different units. And so it doesn't make sense, for example, to compare an uncertainty of a kilogram and uncertainty of a centimeter. So you want to use fractional or percent uncertainties to make those comparisons. And I'm going to use an Excel equation to do this calculation. So starting with an equal sign, and I'm going to use the cell reference, so the uncertainty of F divided by the value itself. And this is displayed just as the fractional form or in decimal form. If you would like to change it into percentage, you want to go about halfway through the middle ribbon here, and you can change it to a percentage. If you want it to show more decimal places, you can increase the decimal here. So usually 2 decimal places is sufficient for looking at your percent uncertainties. And because I want to repeat this calculation vertically in this spreadsheet, I'm just going to grab the corner and drag it down. So now I've just performed all of these calculations very quickly. Now, when I'm looking at the average of the focal length, I'm going to start with an equal sign again. And Excel actually has a built-in function for calculating averages, and that's just the word average. And then inside the brackets, you want to highlight the values to be averaged. So I just highlighted values 1 through 5 and close the brackets. So I have my average calculated here. And to calculate the uncertainty of an average, we actually don't use the calculus method when finding the uncertainties of averages. Instead, we want to look at the statistical average. In particular, the equation is 2 times standard deviation divided by the square root of n, where n is the number of data points. So in this case, I have 2 times standard deviation, which is a built-in function. That can be accessed by taking stdev.s. And then you want to highlight again the values, not the uncertainties, because we want to know how close together or how spread apart this collection of values is. And then to finish off, I'm going to do divided by the square root of 5, because I have 5 values. And that gives me an estimate in the uncertainty of the average. So at this point, what I want to do is compare this result with the results from my measured uncertainties. And note that when you want to report your final answer, so when you're reporting this in your results section, you want to select the uncertainty that is the largest between either the uncertainty from the measurement, so that would be 0.2 in my example here, or the calculated average uncertainty. And so we can clearly see that this value is larger. So I would write my final result with my larger uncertainty here. And just to calculate the percent uncertainty, I'm going to fill this in like so. Switch that over to a percentage. And we can do the same thing for the convex mirror, as well as the average for radius of curvature for concave and convex. Now, there's one extra space after the radius of curvature because we are also going to attempt to verify the relationship between the focal length and the radius of curvature. So the calculation for that uncertainty will be a little bit different, and for that I'm going to switch over to my notepad. So when using the calculus method to propagate our uncertainties, we have the general form here. So if we have a function that we're going to call f that depends on several variables, x, y, and z, then the uncertainty of f, so delta f, is dependent on the partial derivative of f with respect to x. So note this symbol here. This is the symbol di. It is different, although it looks similar. It is different from the delta, which means uncertainty. So be very careful that you aren't mixing up these two symbols because they do mean different things. So we have di f by di x squared times uncertainty of x squared plus di f by di y squared times uncertainty of y squared plus di f by di z squared times uncertainty of z squared. And if there were further terms, then the pattern would continue. Luckily for us, in our first experiment, the only function that we have to propagate our uncertainty through is the relationship between the focal length and the radius of curvature. So that says that f is equal to r over 2. So in this case, our function f is a function of only one variable, which is r. So when we are writing our uncertainty propagation, so delta f, then that's going to be the partial derivative of our function, so di f by di r, which is the first and only variable. That's going to be squared, and then that's multiplied by the uncertainty of r, which is also squared. And that is the only variable, so we don't include any more terms, and then this whole expression is square rooted. Again, because there's only one term here, we can cancel out the square root and the squareds to get something a little simpler. So our delta f becomes absolute value of di f by di r times uncertainty of r. Now, the uncertainty of r will be, in this experiment, you are going to calculate f using the average value of r for both the concave and convex side of the mirror. So this delta r will be the delta r of your average value. So the missing piece is what goes here. Now, what we have to do here is take the partial derivative of f with respect to r. And again, luckily for us, this is the only variable, so that's going to be the same as just the regular derivative of f with respect to r. And we have f is equal to r over 2, so r is the same as r to the power of 1, and so that derivative would just give us r to the power of 0 divided by 2, and then anything to the power of 0 is just 1. So this results in just 1/2. And so our final expression for the uncertainty of f, delta f is equal to just 1/2 absolute value times the uncertainty of r. So anytime you have an uncertainty propagation that you need to figure out in the Physics 1220 lab, I would expect to see these steps written in your lab notebook. So setting up the general form of the uncertainty propagation, showing any derivatives necessary, and then showing the final expression that is used. Once you've determined what expression to use, you can use your Excel spreadsheet to calculate the numerical values. You don't have to show a sample calculation where you plug in a number and get an answer. So using your Excel spreadsheet to calculate the numerical values is sufficient to show your work for this experiment, as long as you actually submit the Excel spreadsheet with your lab work. So when an Excel spreadsheet is used, make sure that you are submitting that along with the rest of your lab work.